friends, and welcome back to the reading on time series analysis. So the first module we're going to talk about is linear and log linear trend models. And the time series analysis reading is still using linear models in developing a relationship or analyzing a relationship. One of the big things here is that you don't use independent variables per se. Instead, you are using past values of the dependent variable, the y variable, to forecast the future. So in other words, we are just doing something similar to technical analysis, whereby we are demystifying an existing pattern in our variable of interest. So for the purpose of this reading, we are going to do away with the label y for dependent variable. Instead, we are going to shift to variable x. It doesn't matter what label I use. We are still trying to do forecasting using a linear model. So the first thing, the reading is divided into two parts. The first part talks about the trend model, which is really, really simple. It is nothing other than simple linear regression that we learned at level 1. Remember simple linear regression? There is only one x variable. So the independent variable is a time index. And this time index takes on a value progressively higher. So it goes from 1 to n in your sample size. So n being the sample size. So starts out with the index of 1, then moves on to 2, and so on and so forth. So we are not concerned about 1990 and 1991 as time index. Instead, it starts always at index value of 1 in our sample, and then moves on to index value of n. As we move out of the sample for the purpose of forecasting, then you do the same. You keep on incrementing the index value by 1. So you have two models, linear and log linear. Log linear models are used for non-linearity in the variable of interest. Here we label it as the x variable, but remember we traditionally called it the y variable. So if the variable of interest has some non-linearity, some, not all kinds of non-linearity, but some of the non-linearity can be modeled using what is called as a log linear trend model. We'll talk more about that. The focus here, though, is AR models or autoregressive models. So we'll spend a lot more time on that component, at least as far as the exam is concerned. All right. So time series analysis. Time series is simply a data set, a set of values that is collected over time. And two attributes is the time period involved is fixed. So if it is monthly, it is always monthly. If it is daily, it is always daily. Is annual, it is always annual. So it can't be one observation is a daily observation and the other is monthly observation. So fixed time period. And then secondly, you're not skipping any time period. There are no gaps in your series. So that is a time series, and here are some examples. Quarterly sales over last 5 years. So n is equal to 4 being quarters in a year times 5 or 20. Monthly CPI over 12 years, you will have 12 months in a year times 12 years or 144. And then daily returns is 1 times 180 is equal to 180. So these are just simple examples of what time series is. And what you are trying to do is to demystify the pattern. If your sales follow a specific pattern, you want to be able to forecast sales going forward using what you've already seen in the past, using the pattern that you already observed. So the model is first we start with the linear trend model. Your yt is equal to beta naught plus beta 1t plus et. Now for trend model, we're still keeping with y as the dependent variable. When we go to AR models, we will go with x as the dependent variable. The label, as I said, doesn't really matter. Now, sample, the independent variable is t. So remember, independent variable was the x variable. Here, always independent variable is t. And there is only one independent variable. So only one variable on the right-hand side. There is only one beta coefficient on the right-hand side. So the time index, again, takes on a value of 1 through n. Always start with value of 1 for the first observation. Again, if I'm trying to forecast, so the next observation, t is equal to n plus 1. And the second observation after that is n plus 2, and so on and so forth. Now, one takeaway from this regression model is the predicted change in y is the slope coefficient beta 1. And this is a model that can be used when your y variable, the variable of interest, has a constant change in its value, an expected constant change. So there will be some error, there will be some noise, but if your unit, if it is increasing by constant amount, then you can model it using a linear trend model. So if revenues are growing by 50 million every quarter, approximately, then you can use a trend model to forecast revenues. All right. So supposing you fit a linear trend model and you find that the estimated intercept term is 0.95 and the slope coefficient turns out to be 2.5, you're asked to calculate forecasted value of y for t equal to 1 and t equal to 2. Here, this is within sample forecast, meaning we are looking at the first observation and seeing what the forecasted value of that first observation is. Then, of course, we can compare it to the actual value because this is within sample, and determine what the noise term is, what is the error value. So it is simple plug and chug, just like you did predicted value y in multiple linear regression. Here it is simple linear regression with only one x variable, and that one x variable is the time index. So you plug in a value of 1 and 2 in this equation, and you notice the change is equal to 2.50, so 5.95 minus 3.45. And that 2.50 is not a random occurrence, it is simply the value of beta 1. Again, these are predicted values. The actual values may change by more or less than 2.5, but at least our forecasted model, assuming the model is good, is telling us the change should be approximately equal to 2.5. Now, log linear trend model, again, as I said, if the underlying y variable has some non-linearity, specifically if it is exhibiting exponential growth. When I use the term growth, doesn't necessarily mean the series is growing positively, it can be growing negatively also. So growth can be positive or negative. Typically, we use the label decay for negative growth, but it doesn't matter. We have to use the label growth here in a very generic sense without any directionality. So what you, in that case, if there is an exponential growth, remember exponential growth is described by e raised to x, and e is the Euler's E. So e raised to x, and x is this beta naught plus beta 1t. That is what we are modeling. We are looking at a specific rate of change in that dependent variable. Instead of amount of change, it is a rate of growth or rate of change. And so we take the natural log of both sides of this equation and we get this model, this equation. So before we start fitting the model, we first take the natural log of the y variable, the variable of interest. First take natural log, and then after taking the natural log, if you look at the right hand side, it's exactly the same as a linear trend model. So you're basically using the same approach in estimating your regression parameters. You are basically doing the same as a linear trend model. Your computer software is going to generate estimates of beta naught and beta 1 using the same approach. So you transform the data manually first and then feed the data into your software package. So now the interpretation of beta 1 is the growth rate or constant rate of change. That is the interpretation of the slope coefficient in a log linear trend model. All right, so supposing your model quarterly net income, and supposing you're estimating it to grow at 18% every quarter, and this is the model that you got. So after taking natural log of the net income for every quarter in your sample, you get your model is fitted, and you get estimated beta naught as 5.75 and beta 1 is 0.18. So now you're asked to estimate the value for the 27th quarter. So you just plug in 27 for T, and you get a value of 10.61. Now that 10.61 is the predicted value of log of net income in 27th quarter. We are not interested in log of net income, we are interested in the value of net income or estimated value of net income. So to estimate the value of net income for the 27th quarter, we are going to do e raised to 10.61. So you're going to use, in your calculator, you have the ln key, you use shift ln. So ln stands for natural log, so if you want to take log, use the ln key. But if you want to take the exponent, which is inverse of it, you use second function ln, which above that ln key you will see e raised to x. So put in 10.61 and shift ln key, and that will give you out to be 40,538. So that is the forecasted value. 10 point, double checking. Yeah, 4538.20. So that is the forecasted net income for the 27th quarter. Remember, the first quarter is always the first observation in your sample.
Okay.
So to compare the two, graphically, if your data set shows, if you scatter plot, so forget the label here on the top for the time being. If your scatter plot shows basically a linear trend model would fit well, so a straight line would represent the graph better, then you use a linear trend model. But if your graph is showing, if your scatter plot is showing it curved, then a linear trend model is not going to do a good job. In that case, you take natural log of the y variable. After you take the natural log, your data is transformed. So this plot uses log of y, and now you see a linear model being fitted to the variable log of y. Now, in trend models being fitted, to the variable log of y. Now, in trend models, the error term, the residual, should not be correlated. There should not be any serial correlation in residual. And it is extremely important in the case of time series models, all time series model, that the residual term should not be correlated. Any serial correlation in residual will be problematic Durbin-Watson test to identify serial correlation. Remember, Durbin-Watson is for one lag only.
Okay.
This reading is focusing only on one lag. So that is what the curriculum is prescribing using Durbin-Watson statistic. When we go to AR models, you will see that one lag is not going to be okay, and we are not going to be using Durbin-Watson statistic. So trend model are nothing other than regression models, linear regression models, simple linear, in fact. So we can use Durbin-Watson statistic to check for serial correlation. So if there is serial correlation, then we basically revise our model or try a different approach, a different model. All right, so that is it. Very shallow coverage of trend models. We move on to AR models in the next session, in the next module. All right, welcome back, friends. We are ready to talk about autoregressive models, more advanced time series models. And there are 6 learning outcome statements. So that tells you really the focus of this reading is in AR models. Okay, so we start with the basic form with only one lag. And notice again, now we are switched from the Y variable to X variable. The label doesn't matter. One variable we are using. So we are looking at lag values or past values of that variable to forecast, to generate a relationship, to model a relationship, and that helps me generate a forecast for the variable. So if there is systematic pattern in the underlying variable, then we are looking to demystify that pattern. We are looking to model that pattern, to put it on a equation. So that is your AR1 model. We'll focus on AR1 model for a lot of things in this reading, but we also need to know the generic model, which is with the P-lags. So once again, even though we are using P independent variables, remember we used the label K before, but here we are using P. It doesn't matter. P denotes the number of lags. Statisticians like the label P, the alphabet P, to denote lags. And we saw that also in multiple called a AR model of the order P. So order P AR model. Okay, that's the label. That's just a term that is used by statisticians to describe an autoregressive models. So once again, we are now doing away with the label Y for the dependent variable because there is no independent variable. So we just use generic X to denote both dependent and independent. And the model is looking to essentially establish a pattern. It's using only the past value of the variable to explain its variation, to explain the variation in that variable. Now, one of the key requirements of an AR model is covariance stationarity. Fancy label, but the idea here is the underlying pattern in the X variable, in the variable of interest, should be constant. It should not fluctuate. If the pattern changes, then obviously what your model captured is not going to help you forecast the future. So requirement is that what you see in the past is going to reoccur in the future. The past is representative of the future. That is what we mean by covariance stationary. Now, covariance stationary means it has a constant mean, variance, and covariance. In fact, if the covariance is constant, implicit in that statement is that the mean and variance is constant. Now, a non-stationary time series will produce meaningless results, will be useless forecast. Why? Because the pattern has changed. The time series is not static. The movement in X variable is not expected to be the same as what has occurred in the past. So to describe constant and finite expected value, which is a fancy way of talking about mean, let's say you have two time series time and xt, the variable of interest, and if your data set is trending, in this case it is up but doesn't have to be, it can be trending down. If it is trending, it will not have a constant mean. Notice the mean taken over two samples within the data set will be different. So that is not stationary. You want the data set to be having a constant mean. Similarly, if your volatility change, stationary. Now, COVID, variance, meaning the relation, think of it as a correlation between a variable value and its past value, that should also be same. In other words, the pattern is repeatable, it is not random. All right, so now we are looking at a simple AR1 model, and you are given directly that we are trying to predict Intel's gross margin for 2 periods using the model given to us. So beta naught is given to us to be 0.1513, and beta 1, the slope coefficient, is given to us to be 0.7462. So notice you are multiplying that beta 1 slope coefficient by lagged value of the variable. In this case, variable is gross margin. So for t plus 1, given the current gross margin is 63%. So plug in the value of 0.63 in our model, in our equation, we get a forecasted value of 62.14%, 0.6214, which is 62.14%. So last period, the margin was 63. Now that we are expecting the margin to come down to 62.14%. Notice we are not using the residual in generating forecast. Why? Because remember, the expected value of residual is 0. So always we ignore the residual term while generating forecast. And I specifically mentioned this because I get a few questions every year about why are we not putting anything for the residual while the expected value is 0. And same thing for doing the same thing going forward. Now, for t plus 2, remember the forecasted value calculated for t plus 1 is 0.6214. So this is stepwise forecasting. We are using the forecast generated in step 1 as an input in step 2. And we get 0.6150, even down more. I'll explain this this movement in a little bit. Why is the gross margin forecasted to decline? And when we get to mean reversion. But I'll define the mean reverting level here. So MRL is equal to 1 minus beta 1. Sorry. So 1 divided by 1 minus beta 1. So it will become 1 divided by 1 minus beta 1 is 0.7462. And 1 minus 0.7462. Reciprocal is sorry, not 1 divided by, I was mistaken. It is beta naught over 0.7462. Beta naught is 0.1513. So 0.1513 divided by is 59.5961. And so which is basically 59.61%. So that is the mean reverting level. The definition of mean reverting level is if the prior value is above the MRL, the mean reverting level, then the series is expected, forecasted. Doesn't always occur that way, but we are expecting based on the model However, remember there is a residual term, even though the expected value is 0, there may be a time when it falls below that 59.61% MRL, at which point now it will climb up. So the forecasted value will climb up. So if I were to put in, instead of 63%, if I were to put in 58% in here, I'll see that the forecasted value will be moving towards the MRL of 59.61. So it'll be higher than 58% in the next period. All right, serial correlation in AR models. Now, earlier we said time series serial correlation is problematic. We are basically either not capturing all the pattern in the data, our model is not capturing all the pattern, or worse, we are introducing a pattern in the residual where none should be existing. Remember, the requirement in a standard regression model is that the error term is random and has a normal distribution. Should be noise, random, should not have a pattern. Serial correlation means it has a pattern. Also, we cannot use Durbin-Watson test in AR model. You can use Durbin-Watson in trend models, but not in AR. Common confusion because you're learning so much content that as you move into more and more readings, you forget and you may, come to the conclusion that, oh, you can't use Durbin-Watson for time series. That would be a wrong statement. You can use Durbin-Watson for some time series models, specifically trend model, but you cannot use Durbin-Watson for autoregressive model. Instead, we use a t-test. In a t-test, what you do is you evaluate the statistical significance of autocorrelation or serial correlation. So you calculate the model, generate the residual term, as in your sample. So if you have 50 observation, you will have 50 residual. What is residual once again? Residual is the actual value minus the predicted value using the model you developed. And once you have those 50 observations of residuals, of errors, you calculate the serial correlation in those errors. Fortunately, we are given that information directly. We are not going to calculate those. We are not allowed a laptop in the exam. You should, however, be able to see whether they are statistically significantly different from 0. If they are, then serial correlation is present and it is problematic. So we will look at the testing in just a little bit. Now, the t-test that you're going to use, you calculate a t-statistic. We'll show you how to calculate a t-statistic, and then compare it to the critical t-value from your t-table. Again, on the exam, they'll give you an excerpt of some rows of a t-table, but you need to be able to identify the correct degrees of freedom. In the case of AR models, the correct degree of freedom is t-2. Now we are using the label uppercase T instead of the lowercase n to denote the sample size, but again, it is just labeled, except that here it is time series data. So t-2 is the number of degrees of freedom that is going to get you your critical t-value, as long as your calculated t-statistic is greater than that critical value or less than. If it is negative, it is two-tailed test. If it is less than the negative critical value, then you are going to reject the null, which means there is statistically significant serial correlation. If serial correlation is present, now you need to revise your model. Your model is incomplete, and this is where there is no definitive rule. Model is incomplete, but there is no rule except that what you do is do an iterative process, an art process, that you keep on adding lags until you find that serial correlation is gone. So you revise your model, recalculate residuals, recalculate serial correlation in those residuals, recheck. Statistical significance of those residuals, recheck the statistical significance of that autocorrelation of those residuals, and if it is gone, if they're not significant, then you're done. If not, you keep on revising your model. Sometimes there may be a seasonality in time series data. Oftentimes you have seasonality. For example, for retailers and sales data, you see seasonality in the month of December. So seasonality in data needs to be captured by a seasonal lag. And we'll talk more about that in the latter part of this reading. So here is the testing of serial correlation using a t-test in an AR model. Okay, autocorrelation at different lags is given to us. Typically, in this case, we are given 4 autocorrelation.
Yeah, we're studying. Does CFA get tougher in level 2? Yeah. But I think it's also more fun. What else? Yeah, I think it gets more fun. It's more practical. Um, so okay, I'm gonna cut the live. I'm the only one online. I'm so tired.